Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Hopefully you all are in good health, good spirit, and welcome back to our class after semester break. So before our semester break, we stopped at chapter 4, pulse modulation, where we were introduced to digital communication and we learned about the advantages of digital communication, its compatibility with analog communication, and the transmission methods that involve between digital and analog communications. And we also look at different types of pulse modulation, especially those who are more conventional than PCM. Yeah. And then the sampling theorem, okay, that includes concepts like Nyquist frequency, aliasing, and look at the different sampling types based on the pulses that we use as our sampling signal, which is impulse, our flat top, and natural sampling. And finally, we look at the generation and detection block diagrams for our sample signals. Okay, here we use examples using impulse and also the flat top sampling. Okay, so today we'll continue with the second lecture on PCM, which is the PCM part 1. So in this part, we deals greatly with how to convert from analog to digital signals. And PCM basically involve three main processes: sampling, quantization, and coding. Okay, so sampling is largely based on what we have covered in our last topic. So important thing is that it has to be at least equal to Nyquist frequency, which is 2 FM. Okay, for quantization, there are two types, uniform and non-uniform. For uniform, we have the non-folded and folded types. Okay, for non-uniform, we just we'll go through this quite briefly because it's more complex. So the detailed calculation for non-uniform is out of our syllabus, but we'll go. We look at the compounding concept within non-uniform quantization. For coding, it's just the change from our sample to n-bit PCM bits series. Okay, so let's go to PCM. Okay, so PCM basically is to represent our analog signal that we sampled, and the sampled analog signal then will be represented in terms of digital word, in terms of bit series. So it constitutes three processes: sampling, quantization, and finally coding. Okay, so at the end of this coding process, we'll get the bit series, the series of 1 and 0. Okay, so a more complete block diagram is represented below. So here we have our LPF, low pass filter, sample and hold circuit, and then analog to digital converter. After that, we have line encoder. Okay, so here, what is the purpose of anti-aliasing filter? Okay, so since Fs, okay, we need to make sure that it has to be larger or equal to 2 FM, which is minimum Fs has to be 2 FM. So Fm then has to be limited at Fs over 2. Okay, so that's why we have anti-aliasing filter here, so that Fmax needs to be cut off at Fs over 2. So this is to ensure that there will be no aliasing, and that's why we have this term anti-aliasing filter. Okay, and then sample and hold is where we produced and we convert our analog signals. Okay, instead of continuous time, becomes discrete. Okay, we just take samples at certain interval. Okay, where the gap or the interval between samples is known as TS, the sampling time. Okay, so this is the purpose of sample and hold circuit. Analog to digital conversion, this is where we have our part of quantization and coding. Okay, so all the samples, okay, the samples will be taken at the specific time intervals. And here quantization, okay, we'll have finite levels. Okay, we'll define levels. So from continuous become discrete voltage. Okay, over here is discrete time. For quantization, we change to discrete voltage. So not all sample values will be used as it is. Okay, the values that and the sample values will be rounded to the quantized values, quantized voltage. Okay, so only values that we already defined will be accepted for further process. So this quantized voltage then will be converted to n-bit series. So here is where we have our coding. And then line encoder is the last topic in this chapter. So this is where we represent we represent our bit series into a physical representation that depends on our medium. Okay. So that's it for PCM. Okay, let's look at the next slide. Okay, so for sampling, important thing is that when we sample, the frequency, the sampling frequency that we choose has to be at least equal to Nyquist rate, which is 2 FM. So this is the minimum. Okay. So as for quantization and coding, so quantizer is also known as the amplitude changer because it will round our sample amplitude, round the sample amplitude into a value suitable for coding, where we have already set what are these values based on a fixed number of levels. So this number of levels, we take into consideration the maximum and the minimum value of our analog signal. And the number of levels will be determined by the number of bits used for coding. Okay, so there are a number of terms that I want to introduce. These terms related to quantization that are new to you all. So the three terms, first is quantization level, which is represented by this L, and L is equal to 2 to the power of n. And quantization, n is the number of bits. So that's why you say here depends on the number of binary bits used to represent each sample. If, for example, we set our n is equal to 3, then our level is 2 to the power of 3, which is 8 levels, meaning that we have our code. We have 8 combination of possible codes using these 3 bits. So the first level, for example, is represented by 000, and the last one, the 8th level, is 111. Okay, quantization interval is the magnitude difference between the levels. Okay, so the quantization interval is represented by this delta V is equal to the range, the whole range of our analog signal divided by the number of levels. For example, if our sample signal has 5 volt amplitude and its V peak to peak is equal to 10 volt, then the L is equal to 8. So our delta V is equal to V peak to peak divided by L. So let me just write down the formula. So this is the formula, which is equal to V peak to peak divided by L, where L is equal to 2 to the power of n. Okay, so here our V peak to peak is 10 and our L is 2 to the power of 3, which is 8. So delta V is 1.25. So if, for example, this is our 0, 1. Okay, this is level 0, level 1. So this is delta V, difference between levels. Okay, and the next term is quantization value of quantization voltage, okay, represented by this Vk. So Vk is the middle voltage for each quantized level. Okay, so the equation for Vk, okay, for the lowest voltage, the lowest Vk, for example, if you take this example, n equal to 3, L equal to 8, and our V peak to peak is 10 volt. So for the lowest level, okay, lowest level VKL, this is represents the lowest level, is equal to it's minus 5 plus delta V over 2. Okay, see this minus 5 is our V min. V min plus delta V over 2. So this is formula for the lowest level. Okay. For the highest level, VKH is equal to V max minus delta V over 2. Okay, so this is the quantized voltage of the lowest level. This is the quantized voltage of the highest level. So for lowest level, in this example, V min is minus 5. Our delta V 1.25. So 1.25 divided by 2 minus 5 is equal to minus 4.375. So the quantized voltage for the lowest level is minus 4.375. So any values that is around this voltage value will be rounded to this V naught. For example, if our sample is minus 5, okay, during quantization, it will be